So here is the warm-up problem. We were just going. So the question first is the collision elastic or inelastic? Inelastic. I hear some words over here. Why do you say inelastic? I totally understand. I think you said they're going at. What'd you say?
They're like going the same. They're the same speed, right? Like
the whole time? Or
no, after the collision. Yeah.
Okay. Yes. Okay. And these are the words that you have to be able to put in there, friends. I will tell you that I was grading some of your egg drop things, and as a grader, I can't assume that you know what's going on. You have to say the words that you mean to tell me the physics that you know. So that means that in a question like that, if it said, is the collision elastic or inelastic, and tell me why, you have to tell me after the collision. But that is true. After the collision, they do have the same speed. They're moving at the same speed. They have the same slope, right? So yes, it's inelastic. If you were going to do this on a track with some carts, would you use the Velcro side or the magnet side to make this collision happen? The Velcro side, right? Because they're going to stick together. Absolutely. All right. And then it says, is each cart speeding up or slowing down? So before and after the collision, that's what we're looking at. So let's talk about cart A. That's the first one we're going to do. If you have not, oops, hello, that's not what I wanted. If you are going to, or if you haven't written this down yet, go ahead and do. We'll talk about cart A first. What do you say? Is it speeding up or slowing down? Slowing down, Nolan, why do you say slowing down? Okay. So the slope is less steep after the collision. Okay. And my bonus question for you, because there's always one of those, right? A bonus question. Does the cart continue in the same direction or does it turn around after the collision for cart A? Raise your hand if you think the same direction. Raise your hand if you think turn around. I see more hands for turn around. Why are we saying turn around? Why do you say turn around? Okay, so tell me more words, right? This is what I'm asking. I want you to use the physics that you know. I agree that it's going to turn around. What is it about this graph that tells you that it's going to turn around, or that it does turn around?
After the collision, the line for part A starts going back to originate.
Yeah, that's lovely. Yeah, does that make sense? I saw some other hands. Kimmy, you were going to say something? Was that what you were saying? Yeah, it's another way to say the same thing, right? They're both correct and they're both just fine, but either one works. Yes, but we know that it's going to turn around, and we know that because we've got a negative slope, we've got a positive slope, it's going away from where it started and then back toward. Either way works, but make sure that you understand how to read this graph so that you can make that description happen. All right, let's talk about cart B. Is cart B speeding up or slowing down? I'm hearing both. Let's do some of those. Or actually, I don't want to vote yet because that's kind of scary. Talk to your table mates. Go right now. Cart B, is it speeding up or slowing down? All right. Do you have an answer now that you've had a chance to ask somebody? You've had a chance to discuss a little bit? Raise your hand if you think it's speeding up. Slowing down? I see lots of hands. Piper, can you give me a reason that you think that it's slowing?
The slope is steeper before the collision.
Cool. Yeah. So B is also slowing down. And again, it's because the slope is, you said, steeper before the collision? Awesome. Bonus question time. Is cart B turning around or going the same direction the whole time? Same direction the whole time. How do you know it's the same direction? Go, Olivia. Velocity is always positive. That means it's always going away from where it started, right? Yeah, yeah. So it's going to go the same direction. Look at all of that physics you guys know. All from this little graph here. We are going to continue looking at graphs like this. We're going to continue looking at your lab graphs that you made yesterday. This is what I would like you to do right now, okay? I would like for you to take all of your things with you, but you're going to keep your lab out, okay? And you are also going to have one person from your lab group, your pair or trio, come up and get green sheets for everyone as well, okay? Go ahead and move to your lab spot. If you are not in a lab, come up to me and we can figure this out, okay? And I'm going to give you just a minute to get there, and then we will regroup. Go, go, go. Hello. Just a second. So, friends, we're going to take a look at the front of the sheet to start, okay? It looks like this. It's the one that has the names. You can put your name on there if you would like to, okay? And we're going to look at 3 specific collisions today. So yesterday you got to do a lot of experimentation. There's lots of different kinds of collisions, and you got to kind of pick what was going on. I would like for you to have that yellow sheet out so that you can use that to build on, okay? And right now we're all going to focus on collision A together. So collision A is an elastic collision. Collision A uses 2 carts with the same mass, and one of the carts is at rest, okay? What I would like you to do right now with your lab partner is to try and draw the graph before and after the collision, okay? Based on what you know, based on what you saw yesterday, okay? You may have done a graph just like this. So you can take a look at your yellow sheet and see if you did, okay? Go ahead and get started with that. I'm gonna give you just a couple minutes to try it out. Let's take a look at what we know so far. So I think some of you have done this. Some of you have a good sense of what's going on. Some of you may be like, I'm not really sure. But let's take a look at the beginning, the before part to start. Okay, so it says it's an elastic collision. They've got the same mass, and the thing we really care about from the beginning part is the one at rest. If you have one cart at rest, how are you going to represent that cart prior to the collision? What are you going to do? Straight horizontal line. Does that make sense? So if you don't have that yet, go ahead and do that. You've got a straight horizontal line. Okay, there's one of the carts. Okay. Is the other cart at rest as well? It wouldn't be a very good collision if it was at rest, right? So the other one's got to be moving. Do we know which way it's moving? No. So we get to pick. Who wants to pick today? You want to pick me? It's going negative. Okay. So it's going down, right? The slope is going to go down. So that means we've got a slope that looks something like, whoa, hi. There we go. Let's try that again. Bam, something like that. Okay. So I'm going to draw it this way because Nate told me to. If you would like to draw it as a positive slope, that's 100% fine. Not wrong. You do you, it'll be fine. This is what we know so far. Some of you did this experiment yesterday, and so you know what's going to happen. Some of you didn't. Either way, what I would like for you to do right now, after you've given it a good guess, a good educated understanding, is that I would like you to go over and get tracks. And I'd like you to get carts, and I'd like you to try it out, okay? Go ahead and try it out and see what happens, okay? Make that happen. Just doing collision A, I'll give you just a couple of minutes to try that and draw the picture. All right. So hopefully, with this simple experiment, you found out what is going to happen in this scenario. Again, you used an elastic collision, which means that you used which ones? Did you use the magnets or the Velcro? Magnets because they're going to bounce apart, right? Okay. Same masses. One was at rest. So I've got the red one that's at rest. What happened to the red one after the collision? It bounced? What did it do? It wasn't moving. What did you say, Kelly? You can just tell me what it did. What? It went in the opposite direction. What do you mean? Like, does it go this way or this way? It goes the negative way? Okay, so it moved negative, right? So it started moving. It was not moving. This is, friends, again, this is where we're trying to get the words to describe what we see so that our words are as accurate as possible. So the one that I have drawn is the red cart here was not moving. After the collision, it started to move. And Tyler says that it's going to move and it's going to move backwards, right? So now I'm going to ask one more question. How does the speed of the red cart after the collision compare with the speed of the blue cart before the collision? Did you notice that when you were doing the experiment? Do it right now. It'll take you 30 seconds. Try it out. How does the speed of my red cart after compare with my blue cart before? What do you think? Get it? All right, what do you think, friends? How does the speed of the red cart after compare to the blue before? What did you say? Tell me, what did you guys say back there? Okay, so I'm trying to pull out from what you just said. So the speed of the red one, is it faster or slower or the same as the blue one was before? So because you said the blue is going to stop. Did you guys agree with that? Does the blue one stop and so you have a horizontal line? Yeah? Oops, it's so frozen. See the silly freezing. Yeah, so that's supposed to be really flat and like a straight line. Let me try that one more time. I need to get myself a ruler and a protractor. Oh well, here, let's try it one more time. Come on. That looks more horizontal. So the blue one stopped. We agree? The red one started moving. And you're saying that it moves this way. How does the slope of this line, the red line that's going to come out here, compare with the slope of the blue line before? Same? Looks like it was about the same speed. Same speed means same slope, right? So let's go ahead and draw that. So it's going to look something like that. Does that seem reasonable? Okay. So that's collision A. Let's take a look at collision B. Collision B has very similar specs, except that instead of being an elastic collision, it's now inelastic. Masses are still the same, and one is at rest. Before you try anything out, you can draw the before part. How is the before part for collision B going to compare to the before part for collision A? They will be exactly the same because one's starting at rest and one's moving. If you want to make it a positive velocity now, you can. If you like the negative velocity, that's fine as well. It does not matter. I'm going to go ahead and keep mine as a negative velocity. Or excuse me, yeah, a negative velocity for the one that's moving. So I've got one that's at rest, and I've got one that's moving with a negative velocity. There we go. And once you've got that, again, just like the last one, you can check your notes from yesterday. You can see if you did it, compare, or you can just go ahead and try it out. Try it out and see what happens. Go ahead and do that. Okay, let's take a look. So before the collision, you got this situation. After the collision, what's going to happen? What's going to happen? Yeah.
They like continue in the same direction as the green part of the.
That's perfect. Nice job. They're going to continue in the same direction as the green one was going, but at a slower velocity. How do I represent that on the graph, friends? Smaller slope. Absolutely. Let's do it. So we're going to have a smaller slope less steep slope, but in the same direction. So something like this, and then the pink one will be right next to it. Bam. How are we doing? We okay? Fantastic. We've got one more. Collision C. Here it is. It's elastic. Notice that the masses are now different. Okay? And it says that the less massive car, is at rest. Okay? Quick question before you get started making all your data collection. How's the before collision going to look? It's the same thing again. It's the same, right? Let's do it. Go ahead and draw that if you haven't done so already. Whoa. Okay. Make it happen. If you need more masses, there are masses over there. If you didn't pick any up before, go ahead and do it. Let's do it. I noticed that that orange line does not look very flat, so let me fix that real quick. Whoa, oh my gosh, silly thing. Okay. What happens when they collide? What happens in this case, friends? Go ahead. The red one has a greater velocity than the blue one did originally. Is it going in the same direction that the blue one was going, or does it go the other direction? Like, so if this one's going in the negative direction, is that one going to continue in the negative direction as well? Yeah? Yeah, but it's going to go really fast, right? Because it's less massive. Oh, that's interesting. Yeah, so it's going to go something like this. I'm going to make it really, really fast. Okay. And then what happens to the blue cart? This was the more massive one. Does it stop? Not completely. What does it do? Does it turn around or does it keep going? What's that? I just couldn't hear you. It slows down the same direction. How's that? What's that going to do to your graph? What's it going to look like? Yeah, absolutely. The slope is going to be less steep. So it's going to be something like, oops, like that. That's pretty not steep. Let me fix it. This is why we like to erase things, right? So I can't get it, friends. I am struggling. There we go. Something like this. So this is all qualitative. This is all like us being able to see it, visualize it, explain what's happening. On the back of your green sheet, though, we're now going to start putting numbers to things. Okay? There is a nice program that one can use to find velocities and like actually video. So basically what I did is I videoed these collisions happening, and then I was able to collect data. The technology, unfortunately, is not available to us right now, which is why it's nice that we have this. Okay, so let me introduce you to this graph. This graph, for some of you, is like, oh yeah, I get this. I totally understand. So these little dots are the data points watching those carts as they move. Okay, if you look really carefully, you can kind of see the line where the collision happens. It's right here. So if you want to draw that in, you could totally draw that in. That's where the collision happens. So if you look up here, the green dots, the ones on the top. What's the speed of this cart at the very beginning? It's 0. It's not going anywhere. Time just keeps ticking away, and it isn't going anywhere. So the slope there is 0. And then what happens after the collision? What happens to car 1 after the collision? What's it doing? What's that? It's sped up. Now it's going at a constant speed that is greater than 0, right? Can you tell me how fast it's going? Look at the graph carefully. All the information's there. How fast is it going, friends? 0.348 meters per second. Yes, it's there. Okay. On the other one, cart 2, it's moving at 0.348 meters per second. And then after the collision, it's what? The speed before and the speed after are indeed exactly the same. Okay. We're going to put some numbers to this and do some calculations. We are going to calculate momentum. We did this before winter break. It's been a little while. I know you're like, whoa, it's been a little while, so let's do it. Do you remember what the equation for momentum is? Anybody got that in their brains? Anywhere? I'll remind you that it's a P. Anybody? What might it have to do with? Anybody remember? Have an idea? Yeah. Yes. So that's the equation for the change in momentum, right? Is the because you had the change in velocity times the mass. So, yep. Perfect. You got it exactly. Yes. So to find the momentum at any given moment, you take the mass of the object and multiply it by the velocity. So if you need to write that down, go ahead and do that just so you don't forget. Right? You don't have to memorize. Some people are able to store them in their brains better than others. So thank you for that. I appreciate it. So there's your momentum equation. Okay. It says right up here that both carts have a mass of 266 grams. Well, that's helpful, although I don't really like grams. So we're going to convert that to kilograms. There are 1,000 grams in a kilogram, so this is really going to be 0.266 kilograms. Okay? And using that information, we can now find the initial and final momentum of cart 1. So cart 1 is this top one up here. How fast is cart 1 going before the collision? 0. 0 times 0.266 is, oh, look at us multiplying together. Yes, it is. It's 0 kilogram meters per second. Now, this next one might be a little bit more difficult. You might need to have a calculator for this. So please get out a calculator, every single person. I'm going to take this moment to also acknowledge that I am missing about 3 calculators. If you have a calculator, if you borrowed a calculator from me for ACT, or you just happen to accidentally take one over break or whatever, it's okay. I'm not going to call you out. I'm not going to be, upset. I just would like them back. Go ahead and calculate the final momentum for cart 1 based on the slope, which is the speed or the velocity, and the mass. Go ahead and do that right now. Every single person has got a calculator out. Every single person is punching numbers in. Don't rely on your partner. Don't rely on the other people in your class. You calculate it. What is the momentum of that cart? Once you think you've got a number, then do check with your lab partner. See if they agree. And just to keep things a little bit simple for this process, I'm going to suggest that we always round to the nearest, let's do nearest 1,000. What did you get for the final momentum for cart 1 in this scenario, in this collision? What'd you get? 0.0? Is it 0.09? Yeah. Okay, yeah. So I thought there was another 0. I just want to make sure. It's a little number, 0.0926. I'm going to round to the 1,000th now that we got that extra decimal there and say 9. Is that okay? 2623. Yeah, is that okay? Kilogram meter per second. What does this little triangle here mean? Change in. Change in means final minus initial. So stay focused with me, friends. This is not a hard question. What is 0.093 minus 0? Can you tell me? Yay for you guys listening and making that make sense. 0.093. It is. All right. Meters per second. Can you find the initial and final momentum for cart 2 and the change in momentum for cart 2? I think the answer is yes. And in fact, if you're clever, you may not even have to plug anything into your calculator. Look carefully at it. Think about it. See if you can find it. And once you have done collision A, we're going to use the same process to find the momentum and the change for collisions B and C. Okay? I'm gonna let you do this. This should not take a super long time. Just gonna go through them, plug them in, okay? Find the change in momentum for each cart in each of the 3 collisions. Your goal by the end of the period, or if not, then by the time you get into class tomorrow, is to have finished those calculations and written down a conclusion based on what you found, okay? I'm gonna come around and help you out. Let me know if you need anything, but yes, in fact, you can do this. Every single one of you. Absolutely, you can do it.